He's a professor in astronomy at the University of Leiden. He's famous for his outstanding work related to the European Space Agency's Gaia mission. He got his MSc in astronomy from the University of Leiden in 1991, and then obtained from the same university his PhD in 1996 on the stellar content and evolution of OB associations. He held a sequence of postdoctoral positions, including Leiden, Mexico, ESO in Garching, and then he worked as a research associate at the University of Leiden until 2006, when he became a faculty member at the university, and he's working there since then. Anthony's research interests include mapping of the young stellar populations and tracing recent star formation history in the solar neighborhood, studying the structure and kinematics of nearby open clusters, tracing substructure in the halo of the Milky Way, tracing the sun's birth cluster, and studying the effects of encounters with other stars on the Oort cloud, study of hypervelocity stars. He's also worked on advanced statistical methods applied to the interpretation of astrometric data. And he's involved in astronomical instrumentation as well. More specifically, he's worked on modeling and handling the effects of radiation damage to CCDs on the astronomical space missions, on the attitude reconstruction of the Gaia mission, and on adaptive optics simulations of the Isosyphony instrument. Over the past 20 years or so, his work has really focused on the Gaia mission. His involvement started early on in 1997 with his contribution to the science case for this mission. He became a member of the Gaia team in 2006. He worked at the beginning as a member of the photometric and classification working groups. He was appointed as chair of the Gaia Data Processing and Analysis Consortium, DPAC, in 2012. And he is the corresponding author of the Gaia data release papers. As the chair of the DPAC executive, he is in charge of the overall coordination of the activities of about 430 astronomers, IT specialists, project engineers, and so on all over Europe. In 2018, Anthony was one of Nature's 10, that is one of the 10 people who were considered by the Nature Science Journal to matter the most in science for the year 2018. So that's a very important distinction. In 2019, he gave the prestigious Spitzer lectures at Princeton University on the subject of the Gaia mission. He also gave the Angstrom lecture in Uppsala University in Sweden the same year. And in September 2020, the Air and Space Academy has awarded to Professor Anthony Brown its Grand Prize 2020, together with Vincent Ponsignon, the Gaia Satellite Project Manager at Airbus Defence and Space, for their decisive contribution to the success of the scientific space mission of the Gaia satellite. So with these very few words, it is a great honor and pleasure to have Professor Anthony Brown with us today. He will talk to us on the Gaia mission and Gaia EDR3 science highlights. Anthony, the floor is yours.
Thanks, Despina, for this very nice introduction, and thanks also, Maria, for the invite. It's a real pleasure to be here. Well, here in my in the top floor of my house, but virtually in Athens. So let's hope I can make it there at some point in person. So okay, let's get going with the talk. So this is about the Gaia mission, of course, and with a focus on science highlights from the various data releases that we have put out already, 3 so far, and the next one will happen next year in the second quarter. And I will start with a bit of an introduction as to why we are doing the Gaia mission. So what's the scientific motivation? And this is aimed at, so that also undergraduates can understand. And then I'll give a brief overview of the Gaia mission itself, the most recent data release, and then focus on a few science highlights that have come out of the exploitation of the Gaia data. And I can only cover very few topics. I mean, there have been many thousands of papers published already based on Gaia data, and obviously I cannot go into all of them, but I'm going to just try to give you a flavor of the very broad applicability of the Gaia data. Okay, so in the background, you see an image of our night sky, which was constructed on the basis of the most recent Gaia data release. So in this picture, there are 1.8 billion sources, most of them stars, of course. And what you see here is in each pixel, the summed flux of the stars, taking into account the color, because we are measuring in 3 very broad photometric bands, the colors of these of the stars. And you can see it's really an exquisite image of the night sky. You see the central band, the Milky Way. You can see very clearly outlined all the dust clouds in the solar neighborhood, and the outlines are very sharp because we have so many stars in the background. You also see the Magellanic Clouds. Some of the bright points are actually not stars, but they're globular clusters. And keep in mind that, for example, here in Omega Cen, next to my pointer, there is about 1 million stars or so in the Gaia catalog in that one point of light, and they're all measured by Gaia. So all of them have their proper motion, parallax, photometry, etc. measured. This is just to give you an idea of the very high spatial resolution that we achieve with Gaia on the sky. Now, this is our inside view of our home galaxy, the Milky Way, and of course, what we're after is, you know, since a long time, obviously in astronomy, is what does the Milky Way actually look like when you were able to travel outside the Milky Way and look at it from a distance. We think it looks something like this. This is a very famous artist impression, which was constructed on the basis of data from various surveys, in particular the glimpse survey of the Milky Way plane, and we hope that with Gaia, of course, we can update this image. This is going to take a while to really do this, but this gives a relatively good impression of what the Milky Way looks like if we were able to take a picture from far away. So we are living somewhere over here near the cursor, about 8 kiloparsecs away from the galactic center, which is in the middle of the picture. And of course, you see the spiral arms outlined very nicely in the disk of the Milky Way, which is also where you find the dust clouds, the birthplaces of stars. And then the central part consists of, in general, of much older stars, the bulge, and is one of the oldest features in the Milky Way. Now, the question we want to answer with the Gaia data, which is one of the main drivers of this mission, is first of all, of course, does the Milky Way indeed look like this? Can we reconstruct what it looks like in 3 dimensions and make this picture from outside? And secondly, how did the Milky Way come to be? This is one of the central questions that drives the Gaia mission, is the formation history of our own Milky Way. Now, of course, we do have an idea of how galaxies form, and I show here in sort of a cartoon fashion how this happens, making use of simulations from about 10 years ago by Marie Martic and Frédéric Bourneau. And this is the situation about 1.5 years after the Big Bang in their simulations, where you see on the left-hand side the distribution of gas in the simulation, and on the right-hand side the distribution of stars. And it's been known for a long time already that the galaxies tend to form hierarchically. So you start with the formation of small galaxies, dwarf galaxies, such as, for example, the Magellanic Clouds around our own galaxy. And these small galaxies then, over the course of time, merge together into an ever-growing galaxy. And you can see here the situation about 5 billion years after the Big Bang, where in the gas you can already see the formation of the disk and the spiral arms. And if you look at the distribution of the stars, you can again recognize the spiral arms and the disk of this forming galaxy. But what you also notice is that the outskirts of the galaxy look rather messy. And this is where you have a continuous accretion of these dwarf galaxies going on. And as they enter the gravitational force field of the Milky Way, the tidal forces will tend to pull them apart in these strings that you see over here, or make them more elongated, etc. And in principle, you should be able to find back this type of debris around galaxies, which is what will tell you something about their formation history. And then this is the final situation in the present day, which is where we are finding ourselves. We have a fully formed Milky Way galaxy. And what we want to do is to try to reconstruct this sequence that I have just been showing, what has happened from right after the Big Bang up to the moment that we find ourselves at now. So one of the things we want to do then is look at the outer parts of the Milky Way and try to find some of these the building blocks, in particular ones that were added more recently. But as I'll show later on, you can also find very old building blocks of the Milky Way. Now, how do you do that? So here's a simulation I did together with colleagues in Mexico when I was a postdoc there. And what you see here is 3 of these small galaxies that have been accreted by our Milky Way projected on the sky. And if you see this image, you think, okay, it's very easy to find these building blocks. You just take enough pictures of the sky and you just start looking for the overdensities of stars, and you can identify it that way. However, if you add all the other stars that are part of the Milky Way, then you end up with this picture. So it's a pretty boring picture with just the disk, the bulge, and not much else to be seen. Now, if you look very closely, you can see that there is a slight overdensity of stars over here, the yellow bit, compared to the same region on the sky, on the other end of the sky. And indeed, this corresponds to one of these dwarf galaxies that was torn apart in the tidal field. And here's a turnaround point in the orbits of the stars, which is where they tend to collect together. And that leads to this slight overdensity. But you can see in general that it's pretty hopeless to just take a map of the sky and try to find these Milky Way building blocks. So you have to do something smarter. And one of the things you can do is to, if you collect the radial velocities of all the stars, which is shown here on the vertical axis, so the motion of the stars either towards us or away from us, and you plot that as a function of distance, which of course also have to measure, then again you can very easily separate out the building blocks, the recent accreted material from the Milky Way, from the bulk of the stars. So the bulk of the stars are located at relatively small distances and spread over all possible velocities, whereas these recently accreted objects are still concentrated along orbits, which preserve things like the energy and angular momentum. And that means that stars are restricted to very specific parts of this phase space. So this is just to illustrate in a very simplified manner why it's important that we measure not only where stars are in the sky, but also how they are moving and what the distances to these stars are, so that we can make these kinds of phase space maps and start to untangle the formation history of the Milky Way. So this is summarized in this slide. So one of the central goals of the Gaia mission is we want to understand how did our Milky Way form, and we need to do 3 things to achieve that. First of all, we need to measure the 3D distribution of stars in space. We need to know where they are. This is symbolized by this map of the stars in the very near neighborhood of the sun. Secondly, we need to measure the motions of the stars. So Gaia measures both proper motion and radial velocity. And these motions allow us to detect these streams of stars that we can identify with the building blocks of the Milky Way. Now, all of this is fine, but you can't do very much unless you know how old the stars are and what they are composed of, so their chemical composition. And so we need to astrophysically characterize the stars as well. And this is symbolized by this HR diagram over on the right. And we do that by measuring very precisely the colors of the stars. And we do that in quite some detail because we have prisms on board that can split the light in low resolution spectra. And that allows us to derive things like the temperature and luminosity of the stars, but ultimately also their age and their chemical composition. And those are 2 very important ingredients to make this sort of archaeological reconstruction of what went on during the formation of our Milky Way galaxy. Okay, so that was an introduction then to motivate the Gaia mission, why why this incredible effort and time and money is spent to do all this. And this is just a summary of the mission itself. You see on the top right an image of the Gaia spacecraft as it sits out at the second Lagrange point, orbiting the sun. And in the bottom right, you see the instruments that Gaia carries on board. So there are 2 telescopes. These are the 2 main mirrors of the telescopes. And the light of the telescopes is combined onto a single focal plane, and you can just about make out some of the CCDs in the back here. And this is the way that Gaia continuously spins around its own axis. So these two telescopes sweep out great circles on the sky continuously, and by changing the direction of the spin axis over the course of time, we can cover the whole sky and make our measurements. So the goal is to collect astrometry and spectrophotometry for all objects that Gaia observes, and this is well over 1 billion objects at the moment. We're also collecting radio velocities. This little box down here is actually the optics of the radio velocity spectrograph. So that's a high resolution spectrum made in the calcium triplet region, which allows us to measure the radio velocity. And that can only be done for the brightest subset of stars. So for of the order of 100 million objects or so. The survey itself is complete out to 21st magnitude in Gaia's white light band. And the observing program is done by Gaia itself. It autonomously detects objects and decides which ones to follow up. And over the course of a 5-year mission, every star is on average observed about 70 times. And this means that Gaia is also very interesting for things like variable star studies, for which it's also being extensively used. So it was launched almost exactly 8 years ago, and it has been in operations at L2 since July 2014. And we estimate that the end of life for Gaia will be in early 2025. And this is when the fuel for the micropropulsion system runs out. This is a system that makes sure that the spin rate of the spacecraft is maintained very precisely at 6 hours. And this is needed to make sharp images of the sky. And once that fuel runs out, we can no longer continue the mission. So the mission itself has already been extended beyond its nominal lifetime, which ended in 2019, and we have approved extension until the end of next year. And we're in the process at the moment of finalizing the approval for continuing the mission until 2025, which means that we will have collected slightly over 10 years of data, so doubling the mission lifetime from what was originally planned. Now, just to emphasize again that what Gaia does is it collects really fundamental astronomical data. So we, first of all, have an all-sky, very complete and very high accuracy star atlas. And so this can serve, for example, as a reference frame for many other surveys, anchoring ground-based surveys, for example. You can both astrometrically and photometrically calibrate against Gaia, and that's already being done a lot. Of course, the heart of the mission is to measure the parallax of stars, which tells us something about their distance. And then we make use, of course, of the motion of Gaia around the sun, which causes a change in viewing perspective towards the stars, making it look as if they're executing small circles on the sky. But that's just a reflection of Gaia's motion around the sun. And we make use of that to estimate the distances to stars. Now, because Gaia repeatedly observes stars over the course of time, we can also see that they are moving across the sky, which is a reflection of the fact that they're moving through space. And then when we combine the parallax and proper motion with the radial velocity, which is determined from this type of spectra on the basis of these absorption lines, we of course have the full 3D position and 3D motion of the stars. Now, the photometry by Gaia allows us to study variable stars. This is a light curve made with the white light band of Gaia that we use for the astrometry as well. But in the bottom two plots here, you see examples of these prism spectra, which are collected in a blue band, which runs between about 330 and 680 nanometers, and the red band between 650 and 1000 nanometers. And for example, the blue line over here is for a hot star, B or A type, and you can just about make out the Balmer absorption lines. And the same star is rather faint in the red spectrograph, which is a spectrophotometer, which is not surprising. And there you are dominated here in flux by the late type stars, in this case, Myras, where you can clearly see the molecular absorption bands. So we can use this data to really astrophysically characterize the stars, which is important for these archaeological studies that I mentioned before. And that's symbolized again by this observational now HR diagram on the basis of Gaia data. Okay. So that was it for the introduction to Gaia itself. And just before we continue, I have here a slide with links to reading material if you want to know more. So there's the information on the latest data release, which came out in December 2020. There is a link here to a review that I wrote last year as well, which is on which both explains in detail how Gaia works, and also goes into an extensive set of examples of the science that has been done with Gaia. I also included here a link to the slides that I used for the Spitzer lectures 2 years ago, and you'll find a lot more introductory material there if you're interested. Next year we will have the Gaia EDR3, with lots of new data products coming out. I'll say a little bit more about that later, but you can find a lot of details on what is coming out in that release behind this link. And then if you're interested in, for example, simulating Gaia data in your science studies, you can find links here to on how to do that. Okay, so now just briefly reviewing the last data release that we, or the latest data release that we put out, Gaia Early Data Release 3. This was called an early data release because we only released the new astrometry and broadband photometry, but we did not release all the other data products that we were working out. They're coming out next year, and I'll come back to that later. So the current catalog has about 1.8 billion stars, positions, and white light brightness. And for about 1.5 billion of those stars, we also have their color. So we have the blue and the red magnitude, which you can combine into a color. And for about the same fraction of stars, we have parallaxes and proper motion. So we're almost at 1.5 billion stars at the moment, for which this parallax and proper motion information is readily available for you to use. And then finally, this release also featured a big expansion of our of the optical reference frame, which is materialized by extragalactic sources, mainly quasars and AGN. And this is now also accepted by the IAU as the materialization of the ICRS in the optical. Okay, this is an overview of the performance of Gaia EDR3, the astrometry. So this is the parallax precision on the vertical axis in units of microarc seconds, and as a function of magnitude. And you see here the various Gaia data releases. So this is where we were with Gaia DR1, only a little bit better than 1 milliarc second in performance, down to about 0.3. The blue line is for Gaia DR2, and the green line is for Gaia EDR3. So the latest release has 34 months of data as input instead of the 22 months of Gaia DR2, and that's where most of the improvement comes from, about 30% better in parallax precision. And at the bright end, the improvement is a bit better because we suppressed some of the systematic errors. And then the yellow and the red lines give you the extrapolation to the performance that we expect in Gaia DR4, which will be based on 5.5 years of data, and then DR5, which will hopefully be based on a little bit more than 10 years of data. Now, these improvements are much more dramatic when you look at the proper motions. That's because the increasing time baseline leads not only, you don't only get the improvement due to the better signal to noise, but you get a factor extra in time because of the longer baseline over which you measure the motion of the stars. So here again, you see the various data releases. Now for Gaia DR1, you see this peculiar cloud of points over here. And these were stars that had been measured by Hipparcos already, and we were able to combine their positions from Hipparcos with those of Gaia, leading to proper motions with a baseline of about 24 years. So they were already very precise. And you can see now that with the Gaia EDR3 release, just the slightly under 3 years of Gaia data alone already achieves this precision at the bright end. And you can see how things improve. So from DR2 to EDR3, there's a factor of 2 improvement in the proper motions, really very significant. And we expect another factor of almost 10 going down to Gaia DR5. So there's still a lot to look forward to in these future releases. This is the performance in the photometry, just to give you a quick impression on how precise the broadband photometry is. So the white light band G is taken from the images that were used for the astrometry, and there we are at the bright end, well below a millimagnitude. So the scale on the vertical axis is the logarithm of magnitude. And the blue and red prism photometers, we integrate up their light, and then again give you a wide photometric band. And again, you can see that we reach millimagnitude levels at the very bright end. And these are the photometric passbands of Gaia, with a little warning here that they are slightly different from Gaia EDR3, and keep in mind that things like passbands will keep evolving over the course of the mission as we include more and more data. That's because our instruments slightly evolve, and also things in the details in the data processing change. So that's something to keep in mind if you're interested in very high precision applications of the photometry. Then finally, the Gaia EDR3 also contains radial velocities measured by Gaia, but these are not new velocities. These have been copied over from Gaia EDR2. The only thing that was done was to weed out some of the spurious radial velocities at the extremes of the radial velocity distribution. You see the histogram over here. And that means that if you're interested in looking, for example, for hypervelocity stars or estimating the mass of the Milky Way, you should be very careful in using the extreme velocities from Gaia. And in particular, I would recommend in any case to use the Gaia EDR3 version of this. So next year, we will have many more radial velocities coming out with the DR3 release. And here in the top right, you see an indication of the precision of the radial velocities as a function of magnitude, which is dependent on the temperature of the star on the spectral type. Okay, so now I pass to some of the science highlights that were achieved with the community exploiting the Gaia data. And I want to really try to give you an impression of the broad application of these data. So I start in the solar system, which for many of you might not be an obvious application of Gaia data. And there's various things on this slide. So let me go through this. On the two plots here, the three plots here on the left, relates to this object in the Kuiper belt, Arrokoth, that was visited by the New Horizons mission after it went to Pluto. And one of the things that they did was to use a preliminary version of Gaia EDR2 in order to aid with the navigation of their spacecraft. So they had HST images of this object, where it's of course only a faint point of light, and they wanted to astrometrically determine where it is on the sky to determine its orbit. But they couldn't calibrate it sufficiently accurately against existing catalogs. So they asked us for some help, and we provided them a preliminary version of our Gaia EDR2 for the area of the sky they were interested in. And so Gaia was very instrumental in actually making it possible to navigate the New Horizons spacecraft from Pluto to this other object, Arrokoth, in the Kuiper belt. Now, the other thing they did on the basis of Gaia data is that if you want to plan a mission to an object like this, which is very, very far away, you need to have a good idea of what the size of the object is, whether there's any stuff in the neighborhood that could endanger your spacecraft. So, and this is needed for both for safety, but also to plan the kinds of observations that you're going to do with the instruments you have on board. Now, the only way to do this for solar system objects, or to do it accurately, is really to use occultations. So you wait for this object to pass in front of a star, and then you measure the dimming of the light of the star. And so you see here the occultation trajectory of a star by this object Arrokoth. This was measured in 2017 in South America. And thanks to the precision of Gaia, they could very accurately place their telescopes. And what you see here in the dots are the starting point and the end point of the occultation. And you can see that very nicely it outlines actually the shape of Arrokoth as it was seen by the New Horizons spacecraft. So this is one of the interesting things you can do with Gaia data, is because we have such a very precise star map, which you can use for these occultation measurements. You can actually make out details at the level of about a kilometer all the way in the Kuiper belt, about 40 AU away from us, or even more. Now there's another application, again, having to do with occultations. So this is an occultation by Triton of a background star, which was again very precisely measured thanks to the predictions that can be improved with Gaia as to where you have to put your telescope on Earth. And you see here two light curves. One is from a position in France, and one is from a position in Portugal. And it was on the basis of Gaia data that they decided that it would be good also to measure it from Portugal. And what you see there is that the light dims as Triton passes in front of the star, and then in the middle of the occultation, you suddenly see a very bright spike, and then again the dimming of the light, and then you exit the occultation. Now, this bright spike has to do with the fact that Triton has an atmosphere around it. And as the star passes exactly behind Triton, the light gets refracted through the atmosphere towards us, and this leads to this apparent brightening. And this means that the light curve itself contains information on the atmosphere of this moon. And this is what you see over here in this reconstructed atmospheric profile, where you see the height as a function of temperature. And this is all derived from these occultation measurements. And it means that you can use these types of measurements to make detailed studies of the atmospheres of very distant objects in our solar system. And then finally, here in the bottom right is a result that was presented as a Gaia image of the week, where they took the Apophis asteroid, which is a near-Earth object, and were able to actually measure the way it accelerates, if I'm not mistaken, as a consequence of the Yarkovsky effect. And there have been many attempts to measure this acceleration in the past, and you can see that the old measurements didn't even agree on the sign of the acceleration. But now with Gaia, you get a very, very precise determination of this particular physical effect on asteroids. And this is thanks to the very precise orbit determinations that you can do, again, here also on the basis of occultation measurements. Okay, so now we switch to a very different topic, and this is on white dwarfs. And in particular on white dwarf interiors. So you see here on the top left, the HR diagram of white dwarfs, or the color magnitude diagram on the basis of Gaia data. So you see the absolute magnitude as a function of their BP-Rp color. And one of the surprising things was this split in the sequence of white dwarfs, which you very clearly see over here. That probably has to do with the details of the atmospheric composition of the white dwarfs, maybe in combination with the distribution of their masses. So that's still ongoing debate. But one of the things that was noticed as well is that there is this branch of white dwarfs sticking out over here. Now, what this is a sign of the fact that the white dwarfs, as they enter the white dwarf sequence here on the top left, so just after the star has become a white dwarf, they're still very hot, and over the course of time they will cool down towards lower temperatures and hence redder colors and also fainter magnitudes. But during that cooling down process, at some point the interior, the carbon oxygen interior of the white dwarf will start to crystallize, and that will release latent heat. And that means that the theoretical models predict that in this area of the HR diagram, you will get a pileup of white dwarfs because they temporarily slow down in their cooling. So this was a prediction that was made 50 years ago, and now you can actually empirically directly see it in the Gaia data, this extra concentration of white dwarfs over here. It's also something that is needed to explain the details of the white dwarf luminosity function, so the distribution of white dwarfs over brightness, and the red points are the data, and the lines are various models to explain these, and these are used, for example, to try to estimate the disk of the age of the disk of the Milky Way. But in order to really understand the details of this luminosity function, you need to invoke this crystallization. And what's more, the crystallization is not sufficient. You also, to explain this peak, you probably need to assume that there is also sedimentation of heavy elements taking place in the interior of the white dwarf, through which extra heat is then released. And this is the sedimentation of oxygen-16, but also neon-22 sedimentation happens perhaps by the clustering of these atoms into sort of drops inside the liquid plasma, and that sedimentation then can be seen in the details of the luminosity function. So this is what I think is one of the really coolest applications of Gaia, is that just by measuring very precise distances to these white dwarfs, you can actually say something about what is happening very deep in their interiors, having to do with complicated plasma physics. Okay, then we now come to one of the most surprising results that came out of the Gaia data release 2. Those are the two plots here on the left, and this has to do with the Milky Way disk. And this is a paper by Teresa Antosha and et al. From Nature in 2018. And what they did is they took stars in the neighborhood of the sun, and they simply plotted the speed at which the stars are moving in the vertical direction, so perpendicular to the Milky Way disk. Positive meaning they're moving up, negative meaning they're moving down with respect to the disk. And if you plot that as a function of their vertical position, so how high they are above or below the disk, you would normally expect not to see anything interesting. For a disk in equilibrium, this should be a smooth, almost Gaussian distribution with nothing interesting going on. But if you look closely, you can see that there is a faint spiral structure in this diagram. And if you color code the distribution of the stars by the speed at which they go around the Milky Way in their orbit, so the azimuthal velocity, then you get a very strong signature of this spiral. Now, this was followed up by people working on the Gaia survey. So they took the radial velocities from Gaia in combination with Gaia parallax and proper motions, and they tried to see whether this spiral structure is in the phase space, whether it's visible in the various places in the Milky Way disk around the sun. So each of these panels is for a different position around the sun, different distances from us. And you can see that this really seems to be a phenomenon that is not only happening close to us, but really over the whole disk. And you can see the same effect when you split up the stellar populations according to metallicity, alpha element abundances, age, etc. It's a disk-wide phenomenon. Now, this pattern was never revealed before. It was also not predicted. There were some simulations where in hindsight, people saw that, hey, if I just made that plot, I could have predicted this, but it was really a surprise. And it illustrates why you need very dense sampling of phase space. So why you need to have proper motions, parallaxes, radial velocities for lots and lots of stars, because that's the only way you can uncover these very subtle features. Now, the explanation of this pattern in the phase space is most likely the disturbance of the Milky Way disk by the interaction with the Sagittarius dwarf galaxy. And that dwarf galaxy, well, let me just show what the idea is. So you have the Sagittarius dwarf, which in this simulation came in about 8 billion years ago and went into orbit around the Milky Way. And as it orbits the Milky Way, it passes through the Milky Way disk, and it does that repeatedly. And the idea is that one of the recent passages led then to this disturbing the equilibrium of the Milky Way disk. And what you're seeing here, in fact, is a classical demonstration of so-called phase mixing, where after a disturbance, you get this structure in the phase space, but over the course of time, this will be erased as the stars relax back into an equilibrium configuration. And that's, you know, one of the classical signatures is this kind of spiral structure in the phase space. Now, there's this is the story of the interaction with the Sagittarius dwarf, and there's another way in which you can see that. Well, first, a bit more on this interaction. So if you want to really understand this in detail, you have to make quite sophisticated simulations with high resolution in terms of lots of particles to be used in body simulations. And this is a work by Bland Hawthorne and Tepper Garcia, where they did such a simulation. And what you see in the central panel is the distribution of stars in the Milky Way disk, but also what you also see is the average height above or below the galactic plane. And so the interaction with the Sagittarius dwarf galaxy leads not only to this phase spiral, which you can see when you plot make a similar plot of vertical motion versus vertical position at various places along this simulated Milky Way disk, but you combine that with a so-called bending waves in the Milky Way disk, which means that some parts of the disk are above the average plane, some parts are below. And so you have this combination of this disturbance that you can see in the phase space, as well as this bending wave going around, and this makes it quite complex to interpret the data, and that's why you need these simulations to really understand the details. Now, another way of looking at the same event is to study the color magnitude diagram of stars in the solar neighborhood. This was done by Luis Lara et al. And as some of you will probably know, is that you can actually infer the formation history, the star formation history of the solar neighborhood by modeling precisely the appearance of this color magnitude diagram in terms of the mix of stellar masses, ages, metallicities, etc. that you need to explain the CMD. Now, if you do that and you plot the resulting star formation rate as a function of time in the Milky Way disk, you get this result. So this is the look back time. So this is just after the Milky Way was formed. The star formation rate was rather high at the time, and over the course of time, it will slowly decline. And what the interesting thing is that in between, you see these peaks in the star formation rate. And if you compare that to models of the orbit of the Sagittarius dwarf galaxy, then it's clear that the peaks coincide with times that there was a strong interaction between the Sagittarius dwarf and our Milky Way disk, so when it was passing through the disk. And so you can see not only the evidence in terms of the distribution of stars in phase space, but also when you look back at the star formation history, you get this consistent story of the Sagittarius dwarf galaxy disturbing our Milky Way disk, not only the kinematics, but also apparently triggering star formation. So this is a very nice illustration of how you can apply the Gaia data to come up with this really nice story about this recent interaction between the Milky Way and the Sagittarius dwarf. Okay. This is the last topic I want to cover, and this is about the accretion history of the Milky Way, which is, of course, what I started out with at the beginning of the talk as a motivation, is that we want to understand how the Milky Way got accreted or was formed over the course of time. And what you see here is the results of the analysis of proper motions based on the first Gaia data release combined with the Sloan Digital Sky Survey. And this combination allowed the derivation of proper motions at that time, which were not yet available for the very faint stars, which would only come available with Gaia EDR3. But by making this combination between these two surveys, you could already look for proper motions of faint stars. And what you see here are plots of the velocity distribution of those stars split up according to various metallicity bins. So this is essentially the radial motion with respect to the center of our galaxy as a function of the azimuthal motion. So again, the motion at which stars are going around the Milky Way. And in particular in this metallicity bin over here, so around minus 1.1 or so, you can see a clear single blob of stars that are mostly coming from the disk. And then there's also a distribution of stars over here that are hardly rotating. So they have a very low, very low rotational velocity, which is I said it earlier, the wrong way around. So the vertical axis shows the rotational velocity of the stars around the disk, and the horizontal one, the radial motion with respect to the galactic center. So whether they're going in or out. And you can see here this population of stars that is very spread out along the radial motion direction with hardly any rotation. And they named this the sausage after the shape at the time. And the hypothesis here is that this is the stellar debris in our inner halo of our galaxy, which was deposited a long time ago, about 8 to 11 billion years ago, during a major accretion event from a substantial satellite. Now, with Gaia EDR3, this picture became much clearer and sharper. And one of the interesting things that was pointed out in the paper that presented observational HR diagrams on the basis of Gaia EDR3 data is that if you look at stars that are moving very fast with respect to the solar neighborhood, with respect to the sun, and make an HR diagram of stars in the wider solar neighborhood, then typically at these velocities, you should be picking up stars in the halo of our galaxy, so the oldest populations. And what was noticed there is that there is this very clear split in the main sequence in a blue and a red sequence. Now, at the same time, there was an analysis done by the group in Groningen, led by Amina Helmi, where they took the stars in the Gaia data and they plotted again on the horizontal axis. Here is the rotational velocity of stars around the Milky Way disk. So these stars are sitting here at around 200 kilometers per second. And on the vertical axis, you see essentially the velocity dispersion in the other two components of the velocity. And so here in the bottom right are all disk stars, so they're mostly moving in circles around the Milky Way and have hardly any other velocity dispersion. But when you look at the rest of the distribution of the stars, and in particular this cloud of blue points, this represents a population of stars that has a very large velocity dispersion and also seems to be not rotating, so they're around zero, or even counter-rotating, so rotating in the other way around in the Milky Way. And in the right panel, you see for the same plot, but for a simulation that was done more than 10 years ago, where they simulated the effect of a massive satellite being accreted by the Milky Way, and what would it look like in this kind of phase space diagram. And you can see that the two look very similar, which immediately hinted to them that indeed with Gaia, they had now seen this massive accretion event. So this was studied further by looking at the chemical compositions of the stars. You see here the alpha element enhancement as a function of metallicity, and the blue stars, so over here in this cloud of points, are mainly along a sequence that you don't find much in the Milky Way, and it points to something that was formed outside the Milky Way and hence accreted. And basically this blue sequence of stars in this HR diagram then is identified with stars that have been accreted in the past, whereas this red sequence coincides with stars that were already in place at the time that this merger took place. And so the conclusion was that, again, about 10 billion years ago or so, a very massive satellite was accreted by the Milky Way. At the time, the Milky Way itself was also smaller. And so we are talking about a 4-to-1 ratio merger. So it's not yet maybe a major merger, but it's a very significant merger. And of course, this galaxy came with its own population of stars and also globular clusters. And you can see here the distribution of the stars that were accreted 10 billion years ago on the sky based on the Gaia data, with some of the clusters, globular clusters, identified that might have been brought in by this galaxy at that time. So this has been a really very significant event in the life of the Milky Way, uncovered thanks to Gaia data. And the name given these days to this accreted satellite is the Gaia Enceladus galaxy. Here's a bit more on the accretion history of the Milky Way. This is work that has been done by Anna Bonazzi et al. On the basis of the H3 radio velocity survey. So this is a survey that's done in the US to collect the radio velocities for stars, a lot of them in the halo of the Milky Way. And this allows you to make a diagram like this, where you show the energy of the stars based on their orbits as a function of the angular momentum. And what this allows you again to identify lots of streams where stars that belong together, because they're the same energy and angular momentum. So these are objects that have been accreted by the Milky Way. And what they try to do here is to take these streams and identify them with their progenitors. So try to identify whether these streams are caused by globular clusters that are being tidally stripped, or by small galaxies that have been accreted by the Milky Way. And this identification is done over here in this diagram on the right. Now they went one step further and said, well, we can actually group these so-called progenitors. And I tried to identify actually the host galaxies that brought in this collection of globular clusters and other stream progenitors. And that's what you see in this diagram, where they try to group together some of these progenitors that cause these streams and in that way try to identify individual small or smaller galaxies that were accreted in the past by the Milky Way. And this includes, for example, this Gaia Enceladus, which is this yellowish contour over here, which we've seen before, but you can see that there are quite a number of other building blocks of the Milky Way that have been identified in this way. Okay, and then a recent work that was done by the Gaia team was to try and see if you can use the combination of kinematic information and proper motion and parallax information from Gaia and the chemical information coming from the spectroscopic survey Gaia, whether that allows you to make a chemodynamical separation of populations. So where you can separate out the Milky Way stars from things like the Gaia Enceladus galaxy by using this combination of data. But in the interest of time, let me skip on to the next set of topics, which is a bit of a look ahead at the next data releases. So next year, in the second quarter, we will bring out a Gaia EDR3. And this has a lot of new data products with respect to what we have at the moment in the archive. I've showed you before that we are analyzing these prism spectra in order to astrophysically characterize the stars. And on the basis of those spectra, we will next year provide a couple of 100 million astrophysical parameters. So this means temperatures, surface gravities, extinction, etc. We will also provide those spectra themselves, so these very low resolution spectra, again for a few 100 million stars. And we'll also provide about 1 million stars from the radio velocity spectrograph. And you see an example over here on the right. So this is the spectrum around the calcium triplet region. So these are the deep absorption lines are the calcium lines. But each of the colored bands indicates an element for which you can say something from the Gaia spectra. So you can make quite a lot of detailed chemical composition studies on the basis of these spectra. And so you will get a subset of the stars, you will get the actual spectra, but for many more stars, you will get the details on their chemical compositions. We have radio velocities for about 33 million stars coming out next week. So that's next year. So that's a significant expansion of the radio velocity sample. Many more variable stars together with classifications and their photometric time series. Solar system results, so about 150,000 asteroids along with the astrometry as well as the orbital solutions. We will have a substantial number of non-single stars. By that we mean binaries that you can detect either astrometrically or with the radio velocities or in the photometry, such as eclipsing binaries. And then here is something that the group in Greece is also contributing to a lot, which is the characterization of quasar hosts. So these are sources that are observed by Gaia that appear point-like, but where you can just about make out the faint galaxy around it, as well as galaxies themselves. And these prism spectra have also been employed by the group in Greece to say something about extended objects, such as galaxies, looking at their spectra and trying to characterize them as much as possible. And then finally, we will also bring out, as a taster of data even further into the future, the so-called Gaia Andromeda photometric survey. And this consists of the photometric time series for all sources in a 5.5 degree radius field around the Andromeda galaxy. So not only of the variable stars, but also stars that we think are not variable, but we provide this as a taster for what is coming in a future release in DR4, while we plan to release the time series for all sources. This is just a preview of the things you can do with the BP and Rp spectra. So on the left, you see again examples. These are simulated examples of what these spectra look like for different types of stars. So again, things like O and B stars are very bright in the blue prism photometer, whereas in the red prism photometer, it's the cooler giants that are dominating. And you can see, again, you can see clearly their molecular absorption bands. Now, on the basis of the shapes, the detailed shapes of these spectra, Spectra, you can say something about the metallicity of the star, and even try to say something about the alpha element enhancements. That's just a very subtle feature. And you see over here the distribution of stars in the galaxy. So the height above the plane as a function of the galactocentric distance, this is the position of the sun. And you see, of course, the expected trend, namely that close to the disk, the metallicities are high, and as you move away from the disk into the halo, you get to lower metallicities, and you expect to see the opposite trend in the alpha element enhancements, and that's indeed what you see in this diagram. So this is just a foretaste of what you can do with the information coming from these spectra, which, as I said, we will have for hundreds of millions of stars. And this is something, again, using these spectra, these low-resolution prism spectra. And these are spectra of quasars that were observed by Gaia in the blue and in the red band. And some of the emission lines, well-known emission lines of quasars, are identified in this diagram. And these have been ordered by redshift and plotted in the rest frame wavelength. You can very nicely see that as the redshift increases, that the wavelength shifts, and also that the spectra contract due to this effect of going to higher redshift. So again, this is a sampling of the types of data that will come out next year that you can use for your science. Okay, looking further ahead into the future, this is a look at Gaia EDR3, which we don't expect to come out before the end of 2025, because we need quite some time to process it. We have already started working on it, and it includes 66 months, so 5.5 years of input data. And we expect the overall gain in astrometric precision to be 40% for parallaxes and about a factor of 3 for proper motion. So in particular for proper motions, this is again a very significant improvement. Now, this is a list of the foreseen data products, where very notably we will put out also time series of these XP spectra, and you see an example of what you can do over here on the right. These are spectra of Mira stars. This is a carbon-rich Mira, and this is an oxygen-rich one. And the spectra have been color-coded according to the pulsation phase of the star. And you can very nicely see how the spectrum changes as the star pulsates. So this is just one of the things that you could start doing when you have these time series of spectra. We will also expect to be putting out of exoplanets with Gaia detected primarily through the astrometry. And the predictions are that there should be of order 20,000 or so Jupiter mass or more massive exoplanets. And if we go to Gaia EDR3, which will be based on 10 years of data, that number of exoplanets might increase even to something like 70,000. So that's you know, we're not looking at the super fashionable Earth-like planets, but having this enormous statistics on Jupiter-like planets is very important complementary information to understand things like where you might find habitable systems. And of course, the advantage of Gaia is that it's also not biased with respect to spectral type when you make the astrometric detection, where of course for radio velocities, for example, for early type stars, it's basically impossible to find planets. Okay, then looking even further ahead into the future, so this is especially relevant for the young people in the audience if you want to get involved with a space mission. So we put in a white paper for the Esa Voyage 2050 exercise, where Esa is trying to plan out the series of space missions after Lisa and Athena. And the senior survey committee recommended that there should be a focus on either characterization of temperate exoplanets, which involves a rather complex mid-infrared mission, or a focus on the galactic ecosystem with astrometry in the near infrared. So that was on the basis of the proposal that we put in to make a version of Gaia that looks in the infrared instead of in the optical. And this means that we can go much deeper in the galactic plane. And you see here a diagram of the ratio of the number of stars that we predict to see in the infrared as compared to the optical. And you can see that there will be many, many more stars that we can see in the galactic disk. And you have seen before with this example of the phase spiral that it's important to get dense sampling all over the galactic disk to really understand all the details of it. And of course, there's many more applications you can think of when you're talking about a near-infrared version of Gaia. Now, this mission, one of the other reasons to launch this mission is that if you combine Gaia and the Gaia that we have now with a future Gaia in the near infrared, and you make sure that they overlap in terms of sources, then you can actually extend also things like the reference frame to maintain the reference frame to high accuracy for a much longer time, over centuries instead of over decades. Now, there's various challenges that we need to overcome in order to do something like Gaia in the infrared. In particular, you would need to develop infrared detectors that are capable of drift scanning. And if that's not possible, then we have to think about how to realize a revolving scanning mission like Gaia without these drift scanning capable detectors. And if you want to know the details, you can look at this paper where, of course, much more is given than I can cover at the moment. Okay, this is my second to last slide. So just to emphasize again the impact of Gaia on astronomy. So I think one of the most important points basically is that you have now a very large set of easily available fundamental data of stars in the Milky Way. And by easily available, I mean that the DPAC, the Data Processing Consortium, doesn't have a proprietary period. We work only on processing the data, turning it into a catalog, and then it's always immediately made available publicly for everyone in the world. Gaia is an excellent demonstration of the power of an all-sky and high spatial resolution and high photometric astrometric accuracy survey. And this leads, for example, to a dense sampling of galactic phase space. And this dense sampling is necessary in order both to bring out very subtle features in the color magnitude diagrams, such as we saw with the example of the white dwarfs, but also to bring out these very subtle features in phase space. You need to sample lots of stars in order to do that. And this, for example, enables the field of galactoseismology, where you can really study exactly how the Milky Way has been disturbed, how it's responding to disturbances like the Sagittarius dwarf galaxy in order to understand its structure, dynamics, etc. The reference frame that Gaia provides enables very accurate astrometric and photometric calibration of many other surveys. This is an application that is being used a lot. And for example, also the upcoming Euclid mission will rely a lot on Gaia data for its calibrations. And one of the interesting things you can do, for example, with something like Gaia is that you can predict positions of objects in the past, and you can predict it very accurately 100 years in the past. And that means that you can also take very old data and re-reduce them on the Gaia reference frame, and in that way revive lots of old data. For example, if you're interested in studying asteroid orbits over very long periods of time. And we saw also this example of the vast improvement that you get in these stellar occultation campaigns, which allows us to characterize objects at very large distances in the solar system at below a kilometer or so resolution. Okay, this is the last slide. So we are again arguing with Esa for, well, not arguing, we're proposing again to Esa to approve the last extension of the Gaia mission so that we can go on until 2025. And the best argument we can give always is the fact that there are lots and lots of papers being published with the data. So this is something that we're counting on for you to do. And please acknowledge the work that we do by including an acknowledgement in your paper if you use Gaia data. And the other important point I want to make is if you have a nice Gaia result that you would like to communicate and share with the rest of the world, you can go to this website and you can explain what your result is and what the story around it is. And then we can help you to promote that. And it can be done at various levels, from an image of the week on the Gaia website, which we can easily do, all the way to a more higher level Esa press communication, depending on the interest of the story. But this is open to everyone to make use of. Okay, I'll stop here.
Thank you very much, Anthony. It was really exciting talk with many interesting new information, I think. And I believe that there will be questions from the audience because you touched upon many different things. So yes, now it's time for questions. Please either unmute yourselves or you can raise your hand. Or you can even type in the chat.
Can I ask a question?
Of course.
Yeah. Thank you very much for this very nice summary of the results and outlook to the future. What I wanted to ask you is about this near-infrared Gaia, let's say. What is the chance of it? I didn't understand. Is it going to be, I mean, has it gone through the first, let's say, step, or do we know?
Yes, yeah, maybe.
Oops, can't hear you.
So-called senior survey committee, they looked at all the white papers that came in and tried to give a prioritization, but they didn't explicitly mention specific missions as a priority, but rather science teams. And so two of the science teams that they recommended with equal priority were this temperate exoplanets, or the galactic ecosystem with near-infrared astrometry. So that latter one obviously refers to the near-infrared version of Gaia. And that means that it comes very highly recommended by the senior survey committee. But there is this selection to be done between this exoplanet mission or the Gaia Near mission over the next years or so. And Gaia Near was in fact also mentioned as a possibility for a medium class mission. So the top priority would be the large class mission.
Can't hear you, I think.
To take to finally realize it, yeah.
Mm-hmm. Thank you, Anthony, very much.
Other questions? I saw previously a hand raised. Yes, please, Apostolos Mastichiadis.
Yeah, thank you very much for your talk. And if I understood correctly, you have finished with the optical. I mean, there is no reason now to go. You want to go to the infrared because you have to close the chapter with the optical. There is no other information you can get. Gaia is the end of, I mean, you cannot improve on your data, basically.
Yeah, that's not entirely true. We could, I mean, the other option you could consider, of course, is to stay in the optical and try to make it even more precise. So we did quite a while ago, we explored what would be needed if you wanted to go to, say, nano arcsecond astrometry. But that becomes extremely challenging because you're quickly looking at space.
Okay. And there is an interruption now, or?
Yes. The signal is low.
Yeah.
We
lost under. Okay, sorry. It was frozen for a little while. Okay, thank you. And I have also another fringe question. Okay, you have seen billions of stars, but have you seen any neutron stars? I mean, the surface luminosity, because it might be a cooled neutron star, or you can see the tail of the Planck spectrum if it is a hot.
I think I missed part of.
Yes.
Yeah.
Because it was frozen again. I asked you whether, I mean, okay, you have seen billions of stars, but now I am asking whether you have seen any neutron stars in.
Neutron stars, no, not with Gaia. No, they're too faint.
Too faint. Okay.
Yeah. Unfortunately, we might find neutron stars in binaries. That's certainly possible, but of course, they would not be visible. Yeah, but just the question about is it done in the optical? In principle, you could also repeat Gaia just as it is, but let's say 30 years from now. And the combination of the two missions would allow you to derive much more precise proper motions and even parallaxes, and also do much better job on things like binary stars and exoplanets. But of course, if you come with a mission proposal that is the same as has already been done, it's a bit difficult. Yeah. And there are very good reasons to go to the infrared to explore much deeper into the disk of the Milky Way. Yeah.
Okay, thank you very much.
Okay, so are there any questions? Also, I would encourage the optical astronomers, especially in the audience. Okay, I see a hand raised by an X-ray astronomer. Okay, George, you have a question.
Yeah, so thank you very much for the very interesting talk. Yeah, I'm not an optical astronomer, so I have a short span of memory on that, so I'm more focused on what I've recently heard about Gaia. And this was a very nice sum up of everything. So recently I saw a couple of papers that estimated, for instance, the mass of the Milky Way with the latest Gaia data. And of course, like the mass was something about 10 to the 12, depending if you include the LMC or not. And it seems to me like I was looking at that and the history, and it seems that we are sort of like reaching the limit where we have we cannot do any better, as Apostolos may have made, in terms of statistical uncertainties on this problem, while there are some systematics that still occur. And you also mentioned the M31 for the Andromeda galaxy, the new data, and I was thinking that maybe it's too faint for Gaia, for most of the stars, but like, can we do some measurement on the mass of other galaxies, like M31 with Gaia? Have there been any efforts? I'm not sure.
So with for M31, you can actually see the rotation of the galaxy in the proper motions. So if you make averages of the proper motions over the disk, you can actually clearly see the rotation pattern. So this was work that was done by Photometric with Gaia EDR3, and then there is a recent paper. I forget the first name now, but that was based on Gaia EDR3, where again they show very clearly that you can measure actually the rotation of the Andromeda galaxy. Now at the moment that measurement is not super precise, but maybe with DR5, when we have much better proper motions, it would be interesting to revisit that and see whether you can make any pronouncements on the mass of this galaxy based on these proper motions. But then as concerns the mass of our own Milky Way, I think there will still be improvements in the data simply because of the proper motion accuracies that are going to be much better with future Gaia releases. But you are right that the systematics in terms of taking into account the effects of the LMC, etc., that is already clearly much more important than was thought in the past, and that's again something that was learned from the Gaia data. Yeah.
Oh, thank you. And by the way, for the M31, what was the mass that you derived? Do you remember on the top of your?
I don't think they attempted to derive a mass because the rotation measurement is not yet significant enough to make that interesting. Yeah.
Okay. Thank you. Thanks very much again.
Okay, thank you very much, Anthony. Are there any other questions? I suppose that if there are not now, people can still contact you, Anthony, because you shared the slide, so maybe some of the students as well might have questions in the future. So
Yeah, no problem. Of course, you can. You have the link to the slides, so you can have a look at them at your leisure. And if you have any further questions, just email me. No problem. Yeah.
Okay. And there is a comment in the chat. Wow, fantastic! Thank you. So I think that's a good way to close this colloquium.
Okay. Thanks, and
Thank you very much.
thanks again for the invitation.
And
All
hopefully you can come and visit in the future.
Yes, I hope so. All right. Have a good evening, everyone.
Bye. Thank you.
Thank you.